All right, hello and welcome to lecture 9. So today we are going to be looking at energy in electromagnetic waves, and what we are going to assume to start off with is that you already have in the first half of the course looked at the expression for the energy that is stored in electric and magnetic fields. So I'll write this expression down first for you. So the energy stored in electric and magnetic fields from electrostatics and magnetostatics. You should have actually seen this. This is U is equal to integral V del 3x of epsilon naught over 2 E vector dot E vector plus 1 over mu naught, there's a 2 here as well, B vector dot B vector. Okay. If you have not seen this, I would urge you to send me an email and I can discuss this in another supplementary lecture, but this is not going to be a part of the usual thing that we do. Okay. So this quantity that is in brackets, so this is the energy, this particular quantity in brackets is the energy density. And now we will be using this, okay? And what do we want to address in this lecture? We want to address the fact that electromagnetic waves actually will have energy. It'll carry forward energy. This is an important fact because this is the way that we get most of our energy, right? So we get most of the energy from the light of the sun. So we want to understand how to figure out this particular form of energy. So let's say EM waves carry energy. We get most of our energy from the sun. In form of light, or electromagnetic radiation, electromagnetic waves. Okay. So what do we want to do? So we wish to calculate this energy. And as I said, a starting point is going to be this expression above. All right. Now, what do we want to do? So we have integrated this above expression over some finite volume rather than overall space. This is because we want to understand the way in which energy can leave this particular volume. So let's do that. Let's try and understand the change du dt. So du dt is integral del 3v del 3x. Now epsilon naught into E del E del t. There will be two such terms, so of course that takes care of the factor of 2, and 1 over mu naught, similarly B dot del B del t. Now what do? We use Maxwell's equations. Now here we use Maxwell's equations. and hence what we find is that this particular thing becomes integral del 3x 1 over mu naught into E dot curl of B. Remember, we are using Maxwell's equations in vacuum because what we or actually what we will do is not use them in vacuum, but we'll just use them for we'll also put the j term in. So that's E dot j minus 1 over mu naught into del B dot del cross E. So that is what our expression is. Okay. So we have used two of the Maxwell's equations here, and we have not assumed that it's in vacuum, so we have some j. We want to do that because we want to find out what j leaving this thing is. So now another thing that we can do is we can use this following identity, which is E dot del cross B minus B dot del cross E is nothing but the minus of the divergence of E cross B. Okay, this is an identity. Which you can just look at by computing the left hand side and right hand side of this. Okay, this is an identity that we have. So then what do we do? So what we get is du dt is, so the integral v of del 3x, this term, the E dot j term stays as it is, and we have something which is like a 1 over mu naught and del dot E cross B. Again, we have a d3x. Okay. Now the last one, you can use the divergence theorem here to transform what we have into, so this is something which is happening over V. So what you do is you transform this object into a surface integral. So replace this by 1 over mu naught integral over the surface S E cross B and ds. Right. So in the final form, this is what we have. So we have du dt is equal to minus integral del 3x j dot e, that's over the volume V, minus 1 over mu naught into the surface integral of E cross B dot ds, where ds is the surface. So this guy is what we call Poynting's theorem. Okay. First term that we have, this j dot e term, is related to something that's very familiar from Newtonian mechanics. So the work done by a charged particle q moving with a velocity v for a time delta t in an electric field is given by, okay, let me just write this down for you. So work done by work done on a particle of charge q moving with velocity v and for a time delta t in an electric field is given by delta w is qv dot e delta t. Now, so this integral of del 3x j dot e is just is a generalization of this to currents. Okay, so this is simple. So you could think of this as the rate of gain of energy of particles in the region V. So now it comes with a minus sign, so you can just say this is a rate of loss of energy of particles in region V. And this is because, you know, it's sort of there's a minus sign in front of this particular quantity. Now let's reinterpret the equation that we wrote down. Okay, so the equation that we wrote down was du dt. So now let's transport this on the left hand side. I'm sorry, del 3x j dot e is equal to minus 1 over mu naught integral over the surface E cross B dot ds. So the left hand side, so this left hand side is the combined change in energy of both particles and fields in the region V. Since energy is conserved, the right hand side must describe the energy that leaves the surface S of the region V. Okay, for this I'll again write this down. Since energy is conserved, this minus 1 over mu naught integral E cross B dot ds, this must describe the energy that escapes through the surface S bounding the region V. Define a Poynting vector as S equals 1 over mu naught E cross B. This just says it gives us, this is a vector field, it gives us the magnitude of and the direction of the flow in any point of point of space. Now you should not confuse between this S here and the S that we wrote for the surface, but you know, it's a bit unfortunate that both are named S, but I think you should be fine. Now let's actually look at the Poynting vector, and let's look at the energy carried by electromagnetic waves. So now there is a subtlety that I pointed out very briefly to you when we were first writing these waves down in form of complex numbers. I told you that as long as you are dealing with linear things, this is a very good thing to have. But whenever you are dealing with something which is not linear, like what we are going to be doing now, you can't use the complex complex notations that will lead to wrong answers. So we will just need to take the real parts of it. Okay. So with that caveat in mind, what we will do is we will just quickly try to understand what to do. So let's look at. So we are looking at these waves. So let's have E naught sine kx minus omega t. B is given by 1 over c k cross E naught. That is, of course, the magnitude B naught. The sine k dot x minus omega t. So we are dealing with electromagnetic waves with an arbitrary wave vector k. Poynting vector is then very simply, so Poynting vector is given by S is equal to 1 over mu naught E cross B. If you put this in, and once the dust settles, so this one is actually a k hat is E naught squared by C mu naught k hat sine squared k dot x minus omega t. So this is simply by trying to take the curl. So we are taking the curl of E and B as you remember. E and B are mutually orthogonal to each other, and they are also orthogonal to K. So it's very clear that we are going to have that the electromagnetic wave will transport energy in the direction of, in its own direction of propagation. So EM wave transports energy in its direction of propagation. As you would expect. So one thing that we can do is we can actually look at something which is the average. Let me call this S average. So we average this over a time period t is equal to 2 pi over omega. Then the sine factor just goes away. Sine squared factor goes away, leaving you a factor of half. So then that's E naught squared by twice C mu naught into K vector. So this is, averaged over a time period t is equal to 2 pi by omega. If you do that, this is what you get. And so this is it's actually instructive to compare this particular energy density. No, this particular thing to the energy density of the field. Remember that you had U equals to, this is energy density, which is not integrated over all of space. This is E dot E plus 1 by twice mu naught B dot B. So once you just put these factors in, the dust settles. You see that this is V naught squared sine squared k dot x minus omega t. And if you average this again, so if you average this, this is going to be epsilon naught E naught squared by 2. As you can see, so what we can write is that S average is equal to C U average into K vector. This is an this is a nice thing because you know, so what we have found is that the interpretation is simply that this average energy is equal to the, I mean, average energy density in the wave times the speed of the wave. So let me write that down. Energy S is just the energy density in the wave times the speed of the wave. Which in this case is c. So lastly, what we want to do is we want to relate this to something that we have seen before. So remember that when we had something like del rho del t plus del dot j equal to 0. So this was the continuity equation. For electric charge. What I had stressed at that point of time is that this must hold. So what we stressed at that point of time, not very much, I guess, but continuity equation holds for any quantity that is locally conserved. Okay. So now that we have encountered another quantity that is locally conserved, that is the energy. In Newtonian mechanics, we used to think of this as a single number, but now in field theory, we find it more instructive to think of, I mean, energy density. And this energy includes the energy of both the fields and the particles. So if we do that and we go back to the previous equation that we wrote down, so we had written down du dt equal to minus integral v del 3 x j dot e minus 1 over mu naught integral s e cross b ds, something that we wrote down earlier. So we just see that. So okay, so let me just put this down for a second and write down something else. So energy is also locally conserved, and in field theory like we have, better to think of energy density, that is E of x and t. This includes energy of both fields and particles. So actually, instead of trying to write this equation, let me just take this on the side, write a plus here and put the equal to sign here. So as we said before, so this seems like an integrated version of the sort of continuity equation that we have above. So this looks like an integrated version of the continuity equation. So what we have is, so we can write this as del E del T plus del dot S is equal to 0. So if we do that, so what we can see is Pointing vector S is to energy what the current J is to charge. So this is simply what we have got. So so what I wanted to stress on today is this way of trying to think about how energy is stored in the electromagnetic field and how that is actually transmitted by these electromagnetic waves. So that's essentially it. So what we did is we started off with an expression of energy that is stored in the electromagnetic fields, and then we use Maxwell's equations to derive this boxed formula, which is the Poynting's theorem. And then I told you that you could write so this first term on the right hand side is something which can be interpreted as the rate of loss of energy of the particles in a region V. So the combined change of energy of particles and fields in a region V is given by this form of the equation that we have now in this way. If we did that, and so that was one of our main results, and we could then define Poynting's vector, which was just S, which was the curl of so it was a cross product of E and B. So with that formulation, now we looked at a particular electromagnetic wave and calculated its Poynting vector. We took the average of it, and we found that if you also looked at what the energy stored in this field is, we would find this boxed equation here, that the average of the energy transported by the electromagnetic wave is just the speed of the wave times the energy density, which made a lot of sense. And then we just saw the similarity between the Ponting's theorem and what we did earlier in terms of the continuity equation for the electric charge. Okay, that's it for now. And next class, what we will be doing is we will be trying to understand electromagnetic waves in some medium. But if you have anything to ask regarding this class, please feel free to send me an email. I'd be happy to answer what questions you might have. All right, so that's all for now. Thank you.